We are carrying on with our October-November 2024 paper 42. Right, we are at number 5. Okay, where figure 5.1 shows a pendulum consisting of a metal sphere suspended by a thin string. Thin string means there's no weight lah. The sphere undergoes small oscillation about its equilibrium position. The oscillations may be considered as simple harmonic. Figure 5.2 shows the variation with time t of displacement x of the sphere from its one position. On figure 5.1, draw an arrow from the center of the sphere to represent the direction of the resulting force acting on the sphere when it is the position shown. Right, that's all. Draw the arrow there. That's the marking scheme. The mass of the sphere is 0.15 kilogram. State the amplitude of the oscillation. Okay, what's the amplitude?
1.016.
Okay, just read the maximum point. X. Okay, good. Determine the angular frequency. What formula to use?
Omega equals 2 pi over t.
Right, we can calculate the period. From maximum to maximum is the period. And using omega or 2 pi over t. And round it off to two significant figures. 16 radian per second. Calculate the total energy of the oscillations. Okay. What formula to use?
Half m omega square. M omega square.
Remember your
X naught square.
total energy equals to maximum kinetic energy, no? Half mv square, no? Half mv square, v is omega over x naught. So omega square, huh? Half m omega square x naught square. Put in your value and calculate out. Sketch a variation with x of the kinetic energy of the sphere. That's all it looks like. Maximum must be here. That's where you calculate 4.7. Right? Mine is slightly out. Then amplitude must be correct. Amplitude must be there. Correct. Okay? That's how you are marked. The 3 mark. They will look at the maximum point. They will look at the amplitude. And then they will the curve go this way. Okay, states Ohm's law.
Take Coulomb's law. Oh, yeah.
Yeah.
Force between 2 point charges is directly proportional.
Electric force is directly proportional to the product of the charges
Product of
and inversely proportional to the square of the separation. Right? Between point charges is important. That must be inside there. And combine the two into one sentence if you want to. But that's how they will mark. And on figure 6.1 shows an isolated Figure 6.1 shows an isolated hollow conducting sphere that is positively charged. On figure 6.1, draw a line to represent the electric field. That's all. Going out of the positive charge. That's how you mark at least 4 lines. Radial, that means coming out from the center along the radius. At least 4 significant radial line, approximately equally spaced. Arrow pointing away from the surface of the sphere. You can expect that the question on electric field is going to be non-uniform field. Uniform field is used to be AS, now it's in A2. Earlier years, they test you, but now they are going back to non-uniform field. Figure 6.2 shows a variation of electric field with distance x from the center of the sphere. Determine the radius. How to determine the radius? What's the value?
Uh, 3.2.
3.2. Where the electric field strength inside the sphere is 0. So that's where you read the radius of that point there. 3.2 cm. Calculate the charge on the sphere. How to calculate the charge on the sphere?
E equals Q over 4 pi uh epsilon x
Okay,
square.
use a
Call it
formula.
epsilon, right?
E equals to Q or 4 pi epsilon naught. R you have already calculated. You have already read. E is there. Then cross multiply to find Q. 4 pi epsilon naught. R change it to meter. 0.32 square. That's your E. 2.2. And then the power 5. Remember the 5 there. Don't forget the 5. Don't be careless. And you get your answer. 2.5 times 10 to the power minus 8 coulomb. Suggest an explanation for the fact that the electric field inside the sphere is 0. Okay?
That's charge. Yeah. That charge placed inside the sphere is pulled equally in all directions.
Positive charge is all the way around the sphere. Right? It's on the surface of the sphere. These are other alternative answers. Charge placed inside the sphere is pulled equally in all directions. If the field was not 0, the charges will move until the field is 0. Field lines go from positive to negative charge, and there are no negative charges inside the sphere. Okay, these are various alternative answers. Define capacitance of a parallel plate capacitor. Okay.
Okay, define ratio of charge of one of the plates to the potential difference between the plates.
Okay. Charge or potential different, or charge is a charge on one plate. Potential is the potential difference between the plate. Can combine them, doesn't matter. It's as you have said, ratio. An initial uncharged capacitor C X or capacitance C is gradually charged, so there is final potential difference between the plate is V and the final charge is Q. On figure 7.1, sketch a variation with charge with PD for the capacitor X as the PD increases from 0 to V. Okay, how does the graph look like?
Going up. No, I mean, constant, sorry.
Straight line through the origin. Straight line starting at the origin, right? And then they were looking at this point. There's a second mark. Any straight line passing through origin will get a point. Determine the expression in terms of Q and V for work done on the capacitor X during the charging process. Explain your reasoning. Work done is the area under the graph. Is half QV. Another capacitor Y is initially uncharged. The fully charged capacitor X in B is now connected to capacitor Y as shown in figure 7.2. The capacitance Y is 3C. Complete table 7.1 showing the expression in terms of Q and V for the final PD across the and the final charge on the two capacitors. Use the space below for your working. Okay, that's a table you're supposed to fill out and now interested in your working. Essentially, conservation of charge we are using. The final charge equals the initial charge. Just redistributed. And Q equals CV. Right? Initially, the capacitors are in parallel. So we add them C plus 3C. Then times your final potential difference. Initial charge is CV. So this becomes 4C. C and C cancel. So VF is divided by 4. Then QX. QX equals CX CF VF. So CX is C, VF is V over 4. So CV is Q. CV is Q. QX equals to Q minus Q over 4 is 3Q over 4. Oh, sorry, I think there's a mistake here. There is a mistake here. This one is CY. Should be CY. Okay, happy with that?
Yeah.
State whether the total energy stored in the two capacitors is less than, the same as, or greater than the energy initially stored in the capacitor X.
Less than.
Why?
Some energy loss, like converted to heat.
Less than. Some energy is lost in the wire, in the discharge. But they didn't ask you anyway. But
Yeah, loss
ask
as
you,
thermal energy can, right?
lost as heat during in the wire, in the connecting wire. Say what is meant by frequency of an alternating current.
Number of complete cycles up per unit time.
What is happening? What have I done? What have I done? Number of cycles per second. Can expect a question on AC to come out. An alternating current I in the resistor of resistance 680 ohm varies with time t according to the I equals 3.5 sine 40 by t, where I is in ampere, t is second. Show that the period of alternating current is 50 meter per second. Remember the general equation for the current. So omega I obtain from here. T is 2 pi over omega, 2 pi over 40 pi. So it's 50 milliseconds. On figure 8.1, sketch a variation of t between t equals 0 to 100 milliseconds. So you must know you already calculate, you should be able to read your peak current as 3.5. Okay, that's the peak value, 3.5. And then it's a sine graph. 3.5 is about there. And then minus 3.5 is about there. And looks like they will look for, what are they looking for? Sinusoidal curve starting from 0. That's where it starts. And initially increasing from there. They're looking at the period 50 milliseconds, and then another cycle, 2 cycle, peak at 3.5, trough at minus 3.5. That's how we get a 3 mark. Determine the root mean squares current, memory work. Root mean squares I naught over root 2. 3.5 is a peak value. So by root 2 is 2.5 ampere. Use your data in B. Include your answer in B part 3 to show by calculation that the mean power in the 680 ohm is half the peak power. So what formula to use? I square R, P equals I square R. Peak power, right? 3.5 is the peak current. 680 ohm resistor. Mean power is obtained from here. Right? 2.47 square times resistance. Roughly about half. If you write out the two significant figure, you get half. Okay,
Okay.
electrons in vacuum are accelerated from rest through a potential difference V to form a beam. The electrons each have a mass m and charge q. The beam is incident on a graphite crystal that acts as a diffraction grating. After passing through the crystal, the beam reaches a fluorescent screen. An interference pattern is observed on this screen. Explain what this observation shows about the nature of electron. Okay, then
Yeah. Diffraction is a diffraction. Wait. Diffraction is a characteristic of a wave. Electron can behave like waves, basically.
diffraction is characteristic of wave behavior. So shows that electron can behave like wave. Implement the expression in terms of mqv for the momentum of the electron in the beam. What formula to use?
EV equals half mv squared.
You can work it out. If you can memorize the formula, go ahead, use the formula of momentum. If not, work it out. qv is half mv squared. And kinetic energy can be written as momentum squared over 2m. That's your AS work. Then cross multiply square root of 2v m over q, m times q, sorry. Okay,
Mm-hmm.
the PD through which electrons are accelerated is now increased to a greater value. Describe and explain the effect of this change in the interference pattern observed. Okay,
Electrons have greater momentum, the smaller the Broglie wavelength and fringes.
basically we are just using these two formula that we have derived and the Broglie wavelength. Electrons have greater momentum, right? Increase in PD, increase in momentum. So smaller the broad increase in momentum, smaller wavelength, fringes become closer together. Electrons are now accelerated through a potential difference V, resulting in pairs of corresponding value of P and the Broglie wavelength lambda. So how does the graph look like?
Straight line up. Yeah, so like a constant,
Right?
quite
Momentum
a steep gradient.
is a straight line, no? Straight line graph. State the name of the quantity represented by the gradient of the line. We are just using the Broglie's equation. Yep. State the name of a quantity represented by the gradient of the line. Your lambda is your x, p is your y, your gradient is h, right? Planck constant. Okay. Radioactive decay is a random and spontaneous. State what is meant by random.
Like cannot predict when it will decay.
Cannot predict when a particular nucleus will decay, okay? State what is meant by spontaneous.
Spontaneous. Like decay is not affected by external environment.
Decay is not affected by external environmental factors. So state one piece of evidence for random nature of decay.
Hmm.
Yeah,
What call like fluctuations, is it? Observed.
fluctuations in measure count rate, right? You won't get a beautiful curve, but your points will be scattered about a curve, the count rate against time graph. Describe the difference between nuclear fission and nuclear fusion. Yep,
Wait, describe what? Describe difference. Oh, okay, okay, okay. Fission. Fusion is like. Wait, I'll go fission first. Small nuclei, no go fission. Splitting, nuclear splitting into two or smaller nuclei. Uh, Whereas fusion is the one joining together to form one large nucleus.
make sure you got 3 points. Large nuclei undergo fission, whereas smaller nuclei undergo fusion. Fission involves one nucleus splitting into two or more smaller nuclei. Fusion involves two nuclei joining together to form one larger nucleus. Right? These are various other alternative answers that the examiner will accept. Explain with reference to variation with binding energy per nucleon with nucleon number, why the process of nuclear fission and nuclear fusion both result in the release of energy. Okay, can
Yeah. Increase in since binding energy per nucleon is greatest for intermediate nucleon numbers.
binding energy per nucleon is greatest for intermediate nucleon number. Right? You can show, can draw your graph. Both fusion and fission involve, got 10 more minutes, involve an increase in binding energy per nucleon. You can draw this graph. Right? Fusion, you have two from here, trying to form that one. There's an increase in binding energy. Fission, you got product from here, break down into two somewhere around here. So there's an increase in binding energy per nucleon. Okay. Any comment? If not, let's go to a new paper.
Oh, this.
Okay, let's go to May, June 2023, paper 41. Found the paper.
Uh, 3, 4, 1. Yeah.
Define gravitational field.
Huh?
Can define gravitational field.
Oh, the direction of force acting on a
Force per unit mass. So define electric field.
well, yeah. Yeah, force per unit mass.
Force per unit charge. So that's all. Force per unit positive charge. And this, be aware of.
Put direction of force acting on a mass. That's at the point.
It should be force per unit positive charge. This one should be force per unit mass. You have to follow the syllabus. Previously, gravitational
Okay.
field, it would be region in space where mass experience a force. Electric field, the same thing. Region in space where charge experience, positive charge experience a force. But now, they've stated in the syllabus, gravitational field is force per unit mass. Electric field is force per unit positive charge. Okay, so be aware that these are formulas given for, for electric potential and electric potential energy. And then gravitational potential energy is given. Gravitational potential is given. Gravitational potential energy is given. State one similarity and one difference between gravitational potential due to point mass and electric potential due to point charge. Similarity.
So I'm
Similarity
lagging.
inversely proportional to distance from the point. Either point mass or point charge. Points of equal potential lie on concentric spheres. Any of these. Zero at infinite distance. Right? Potential is zero at infinite distance. Differences. Gravitational potential is always negative. Electric potential is positive or negative. Right? Because it can be positive charge or negative charge. Okay.
Yeah. Lagging a bit.
An isolated uniform conducting field has a mass m and charge q. Gravitational field strength on the surface of the sphere is g. Electric field strength on the surface of the sphere is E. Show that this one equals to that. So all you need to do is remember your formula. G is Gm over R squared. E equals to Q over 4 pi epsilon R squared. Then divide. G divided by E. Gm squared divided by that. R squared cancel off. So M over Q. M over Q. R squared cancel off. 4 pi epsilon not take down. G take down. That's your equation. Okay. Show that the numerical value of alpha is set. You have to derive, not to derive, then you can show alpha equals to this one. Then put in your value. Right? 1 over 4 pi epsilon naught is 8.99 times 10 to the power 9. G is 6.67 times 10 to the power minus 11. Right? That's it from your data sheet. Okay.
Okay.
Assuming that the Earth is a uniform conducting sphere of mass 5.98 and 10 to the power 24 kilogram, the surface of the sphere carries a charge of minus 4.80 times 10 to the power 5 coulomb that's evenly distributed. Use the information to determine the electric field strength at the surface of the Earth. Give unit for your answer. Right? Just use the equation that you have derived. Right? You want to find E, cross multiply. Take M down, take GQ across there. 1.35 times 10 to the power 20. G is 9.81. That's your M, capital M. That's your Q. That's your Q. Don't worry about negative sign. Get 1.06 Newton per Coulomb. State how the direction of the electric field at the surface of the Earth compare with the direction of the electric field. Okay? Yep.
Surface of the Earth.
One is directed same direction, that's towards the center of the Earth. Okay?
Yeah, like towards the center, right?
Towards the center of the Earth. Okay, now. No,
Yeah.
the charge is negative. Then the gravitational field is towards the center of the Earth. Then if it's negative charge, is also directed towards the negative charge, which is center of the Earth. You assume that the charge are all concentrated at the center of the Earth. The sphere of, anytime we'll cut off lah. The sphere of, a steel sphere of mass 0.2 kilogram is suspended in equilibrium from vertical position in the spring. The center of the sphere is 8.5 cm from the top of the spring as shown in figure 3.1. That's a diagram. That's the mass. The sphere is now set in motion so that it is moving in a horizontal circle at a constant speed as shown in figure 2.2. The distance from the center of the sphere to the top of the spring is now 10.8 cm. Explain with reference to your forces acting on the sphere why the length of the spring in figure 2.2 is greater than that in figure 2.1. Okay? And